Hello and welcome back to All Things Nautical. It's been a while since we've uploaded a video on this channel, and we're carrying on with some navigation, carrying on where we left off. And in this video we're going to have a look at a question from a past exam paper for a rendezvous situation. So in this question we can have a look at the question here. It says you are the on-scene command vessel and two other ships will assist in a parallel track search for a 35-person life raft in 5 miles visibility. Your own ship is steering 050 degrees true, 10 knots towards its starting position, and it fixes its position as follows by GPS. So 36 degrees 25.1 north, 125 06.9 east, and this is all at 6:30 time zone H. Then it says at the same time, so also at 6:30, so that eliminates the problem where normally we get these kind of questions, and the first thing you need to do is make sure that we're basically getting all the ships involved, or all the parties involved. You need to get them at the same time zone to start off this question. So in this case, they are given at the same time. So it says at 6:30 H, vessel A was observed bearing 172 by 14 miles. So that's the position of A at the time when this question starts. So it just gives us an indication where the target actually is, and from there we can then work with what the target will need to do. She will be proceeding at a maximum speed of 14.4 knots, and you need this target then to take up station on your starboard beam by a distance of 3 miles. So in order to basically conduct this search, what's going to happen is this vessel A, and also vessel B, if we look down here, it says 6:30 vessel B was also observed at 315 by 20 miles, and she's going to be taking up station 3 miles on the port beam at the same time as A. So essentially what we want, so we've got this on-scene commander steaming along, heading towards its search point to do a search and rescue, and it's got two ships that's going to be assisting them, and they're each going to take up a position 3 miles off this vessel's beam, one on the starboard side, one on the port side, and then the three ships working together will then start conducting a search. So what we need to do is, the first thing it says, you find the course we steered by ship A. So ship A is given here. We've got a maximum speed for ship A, and we need to find the course to be steered by ship A from 6:30 H. So it's all still in the same time, to then take up station at the required position as required, assuming that her alteration will occur instantaneously at the time. So she's going to be proceeding basically as fast as possible. She's going to be doing 14.4 knots. She's doing a maximum speed, and we basically need the ship to then take up position 3 miles on the starboard beam. Vessel B, on the other hand, will be taking up a position 3 miles on the port beam, and this needs to be done in the same time. So that's very important. We see the same time. So we're not given a maximum speed for vessel B. So for vessel B, it's not asking us to then calculate a course to steer to get to us as soon as possible. It's basically going to say, well, once we know at what time A is going to be meeting up with our vessel, it's going to reach its destination, then we need to make sure then that B needs to then steer a course and speed to actually get to that point in the same time. So typically with rendezvous, we've got two types of questions. So you could have a question where your time of rendezvous is unknown, which in the case of vessel A, that's exactly what it is. So the time of rendezvous is unknown, which is why she's going to proceed at maximum speed to basically get there as soon as possible. And once then we've got that course that she needs to steer, we can then find the time of the rendezvous, which is the next part of the question. And then once we've got an actual time, then it's simply working with vectors then with regards to vessel B to see what does vessel B need to do. So we can then find a course and a speed that she actually needs to maintain to get to this stage. So let's have a look at the diagram. So if we're going to take this is all the information that we've been given in the question. So it says we are in the starting position at 6:30. Then vessel A, also at 6:30, is bearing 172 by 14 miles. So if the unseen vessel is over here, the vessel O is over there, then at a bearing of 172 by 14 miles, we can then plot position A, or the ship A, which is there. So at 6:30, all of this is at 6:30. So this vessel is here. That is its actual location by radar, bearing in range. That's the position then of vessel A. But now we were told in the question that vessel A is not going to rendezvous with the target exactly. It needs to rendezvous with the position 3 miles off its beam. So the target is steering 050 by 10 knots, which means if we draw two perpendicular lines on either side, so we're going to get a vector towards its starboard beam of 140, and we're going to have a vector towards its port beam of 320. So this target A, which is going to take up a position on the starboard beam, is basically going to take up position in the direction 140 from point O, 140 by 3 miles, because it needs to be 3 miles off its starboard beam. So graphically, if we're looking at the diagram, so vessel A is over here, but the point where it needs to meet, or the point it needs to reach, is there. So that's ideally, that's what it's aiming for. So this track over here, this vector that we see over here, A01, is actually the relative vector that needs to be maintained by the target to get to position O. So, and this O we've then moved up, so O, which is the actual target, we're working with O1. So for vessel A, it's going to be steaming or trying to maintain a constant relative bearing with regards to O1. So as long as wherever this ship goes, as vessel A will be moving along its intended track, so this is going to be the intended track there leading up to the rendezvous. We haven't calculated this yet, but that's what we're aiming for. To get to the rendezvous, she's going to get to that rendezvous basically by maintaining this A01 as a constant bearing with range decreasing. So this vector is what we're going to be using in our calculation. And if you plot this on a radar plotting sheet, then this will basically become your new AO, which is this relative vector that needs to be maintained. So for vessel A, that's the case, and that's where she actually is. This is a relative vector. That is the vector of the target, so that's the vessel, the vector that the OSC will be maintaining. So you're going from point O1, basically to point R1 to the point of rendezvous, because this is essentially where A needs to meet up at the time of rendezvous. So we're going to be working within this triangle here. Now, for vessel B, we were told vessel B is bearing 315 by 20 miles. So we can see there 315 by 20 miles to point B. So that's where B actually is. And then it's a similar setup. So she needs to be 3 miles on the port beam. So 320 by 3 miles, which is going to be that point there. So she's actually maintaining a relative vector to O2 in this case. So we've also just moved O up into its port beam by 3 miles, and point O2 needs to have a constant relative bearing with regards to B in order for her to reach that rendezvous position of R2, which will be 3 miles on the port beam of point or vessel A at that point there. So that basically places both of these vectors onto the diagram. So A is going to be heading in this direction. That's going to be a course or a track covered in order to rendezvous with the target. And then this track there will be the track covered by vessel B to rendezvous with the target as well. And this will obviously all be at the same time, as you can see there, with both of these vessels at that time being on each side of the on-scene commander. So that's the information we've been given in the question, and typically this is usually what poses the largest problem for people trying to attempt these questions, is just to take the words we've been, or the question you've been given, and actually putting that into a diagram. So this diagram basically puts all of this into a graphical perspective. And once we've got this, now the next approach we need to have a look at is, for which vessel do we need to take which approach? Because for one vessel, we need to find the time of rendezvous. So the time of rendezvous is unknown, so vessel A. So that is going to be what we're doing first. So we're first going to do vessel A to find this course to steer, which will actually tell us the time of rendezvous, which will give us an indication of the distance covered along that vector as well. And once we've got a distance for that vector and we've got a distance for this vector, vessel B then just becomes a simple combination of vectors in order to find the track BR2. So the formula for this type of question, we're going to be looking at solving this angle over here. So this angle O1A R1, this angle A over here, which is basically the change in course between the relative track there and the track that the vessel needs to steer. So we're going to be looking at this small angle there, and that angle is going to give us the angle that we need to then apply to this course A01 in order to find an actual course to steer. So the formula there we've seen before in class, so the formula, which is the target speed over the own speed of the vessel taking action. So target is the vessel that needs to be met up with, and own will always be the ship that's actually taking action. So it's that fraction multiplied by the sine function of the target's true course minus the target's relative course. Now it's very important that this target's true course and target's relative course, we're talking about the same vessel. So the target's true course, in this case, we can see the target, which in this case is O. So A needs to meet up with O. That makes O the target. And O is moving on a track of 050 by 10 knots. So the true course is 050. Now the target's relative course, in this case, we're talking about this relative vector here. So this is the same relative vector we mentioned earlier, saying this is the vector that needs to remain constant, the bearing that needs to remain constant and can't change. But this vector essentially has got two parts. So it can either be given as the vector A01, or it can be given as the vector O1A. So O1A would be how the target observes the vessel taking action. So from O1 to A, and then the reciprocal of that would be from A to O1. So the own ship taking action, that would be its relative vector, A01. But for the target, then looking back down, for the target, the relative vector would be O1 to A. So that's what needs to go into this formula. So we're looking for the target's relative course there, which is O1A, and we're looking for the target's true course, which is this true course that we've been given in the question. But now we don't know this vector O1A. So what we'll need to do is we need to look at these two vectors and basically add or subtract those vectors to then find the value of A01 or O1A, either way. So in this case, we'll be working with A01 as it's in the diagram here, and then for this formula here, we can just reverse it. We can just then find the reciprocal. So what we need to do is to say, okay, so in this triangle, in this vector triangle here, so we've got from O to A and then from A to O1. So the combination of these two vectors, from O to A to O1, basically those two vectors combined moves from O to O1 essentially. So O01 in this case is the resultant. O01 there is the resultant. So that means that this vector plus this vector must be equal to O01. So now either if you've got a calculator that can add or subtract vectors, you can input your vectors straight into the calculator and subtract them accordingly. Or if you can't do that, you need to work them back to rectangular coordinates. You need to get the rectangular coordinates for that. Then subtract the rectangular coordinates for AO, and that's going to leave you with the resultant AO1. So in this example that we've got here, we've now taken AO1, which we need to work with, and AO1 is going to be the resultant vector, which was O01. It was that 3 miles moving down towards the vessel's beam, minus the OA, which we were given in the question. So O01 minus OA, and that's going to be 140 by 3 miles minus 172 by 14 miles, and that's going to give us then a value of 000 by 11.6 miles. So that means that this vector over here, A01, is going to be 000 by 11.6 miles. So it's pretty much due north. So this vector needs to remain 000, that relative vector. So from O1 looking down, it's going to be 180, and from A to looking up to O1, it's going to be 000. So for the ship taking action, the relative course is 000, and for the target, the relative course is 180. Now the same thing can also be done for vessel B. So whilst we're busy with these relative vectors, we might as well get that relative vector as well. So in this case, it's exactly the same scenario where from O to B to O2, those two vectors combined must be equal to O02. So O02 in this case is also the resultant. So if we're looking at that, then it's a similar type of equation. So we've got O02 minus OB, which we know to be 320 by 3 miles. So in this case it's the port beam again, minus 315 by 20 miles, and that's then going to give us a value of 134 by 17 miles. Now the 2 hours and 8.5 knots we'll get to in a bit once we've actually calculated the rendezvous time. So that gives us this vector over here. Right, so now that we know that this vector over here is 0, 0, 0 by 11.6, that is the value that we can now take down into this formula. So we're going to take that 0, 0, 0, and we know if we can get the reciprocal value of that, so we reverse that value, it's going to give us a course of 180. And that 180 is this target's relative course that we're talking about here. So that's the value that needs to go in here. So it's going to be the 050 for the target's true course minus this new relative course that we've just calculated. So it's going to be the speed of O1R1 over the speed of AR1. So it's basically the target over the speed of the vessel that's taking action multiplied by the sine function then of the direction of O1R1 minus O1A, and this O1A is that 180 that we just mentioned. So we're going to have 10 knots over 14.4 knots, which is the maximum speed of the vessel taking action, multiplied by the sine function of 50 minus 180, and that's going to give us then an angle, a negative angle, and it's very important if you get a negative angle here to keep it as a negative. So this can be stored into your calculator as well, into slot C. I've got it stored in slot C or whatever slot it is you're using. But that angle here refers to this angle. So it gives us that angle there, which is the difference in course between AO1, which is the relative heading for the ship taking action, and the heading that it actually needs to steer. Now, to find this course to steer, so we've now got this new angle, and this new angle we need to use to then calculate the course to steer. And the formula looks like this. So it's the own relative course, so the ship that's taking action, in this case, minus, and that's always going to be minus angle A. So in that case now, then we've got a negative over here, so it's going to be minus a negative value, which means we're going to add them. So we're starting with own relative course, so it's the relative course of the ship taking action heading up in this direction. So it's that 0, 0, 0 that we found earlier. So AO1, which is the relative course, is going to remain 0, 0, 0 basically all the way up until they get to the point of rendezvous. So you're basically trying to create a CPA of 0 with this stage, or with this point here, O1. And as we know, CPA of 0 with range decreasing means a collision, and that's essentially what a rendezvous is. So we're trying to have a CPA of 0 with this point O1. So the 0, 0, 0 needs to remain constant. So the relative course there is 0, 0, 0, and then we'll subtract the negative 32. So if we do that, so it's AO1, which is 0, 0, 0, minus the negative 32, and that's going to give us then an actual course of 032.24 degrees true. So that means that the course that needs to be steered, so this course to steer, this track here, AR1, that course to steer is going to be 032 degrees true by 14.4 knots. So once we've now got that, now we've got a vector here that's got a direction and a speed, but we don't have a magnitude. In this vector here, we've got a direction and a magnitude, but we don't have a speed. And for this vector here, we've also got a direction and a magnitude, but actually we don't even have a magnitude. We've got nothing here except a direction at this stage. So that means that we need to work with the only speeds that we do know, and that's basically going to find, then we're going to use a formula to then find the speed of this vector. As we've got a magnitude for this and we've got a speed for this, and we know what the angle between the two are, we can then by trigonometry we can then find basically the speed of this AO1 vector. And once we've got that speed, we already know a distance for it. The distance was 15.6 or 11.6, sorry. And that speed then we can then relate to the 11.6, and that's going to then give us a change in time, and that change in time naturally will be for this entire triangle, which means we've also got a change in time for this, and that we can use then to find the time of rendezvous. So the formula is going to be, the formula that we'll use looks like this. So it's going to be the target speed, or in this case the target is still the OSC, so it's going to be the speed of 10 knots multiplied by the sine function of the target's true course minus your own, or the vessel's taking action relative course, which is the 0, 0, 0, plus angle A. So this is basically going to be target's true course minus course to steer, isn't it? And that will be over the sine function then of angle A. So just to add the vectors in there again, so it's O1 R1, which is the target, keeping its course and speed, and we've got sine of O1 R1 again, which is the target's true course, minus AO1, which is that 0, 0, 0, plus negative 32. And all of that, this entire function there, over the sine function of negative 32. And that's going to mean, that gives us this formula, or worked formula looks like that. 10 knots times sine 50 minus 0, 0, 0 plus negative 32 over the sine function of negative 32. And that gives us 5.7 knots. So that value there of 5.7, it might also be in some cases you might get a negative. So that 5.7 here, that means that the speed for this vector, so we now know the direction of this vector, we have a distance for this vector of 11.6, and now we've also calculated an actual speed for this vector, and that speed is 5.7 knots. Now that means that if we're going to try and find a change in time, which is a simple time equals distance over speed, we're going to then get distance over speed, which we know is 11.6 over 5.7. So those are your two vectors again. So it's working with that AO1 vector, that 0, 0, 0 relative vector that we found. It's 11.57 over 5.7 knots. And that's going to then give us approximately 2 hours. 2 hours and 1 minute. Just depends on how accurate you worked and how many numbers you use there for your decimal values. That gives us about 2 hours, around about 2 hours. And obviously this 2 hours, which is the change in time, so that's the change in time in this triangle here. So that's the plotting interval, or the change in time for this triangle, which is 2 hours. And we know that all of this started at 6:30, which means if we add that to the 6:30, then all of this gets us to an 8:30 position, which means at this point here, R1 is going to be at 8:30 hotel. So that's going to be the time then of rendezvous. So we've now essentially answered two parts of the question. So we've answered the first section, which asked for the course to steer, and the course to steer we found to be 32 degrees true by 14.4 knots. So that answers that part. And now by finding the speed for this vector and comparing that to the distance of that vector, we found a 2 hour interval, and that got us to the point R1, which we know to be 8:30. Now if this is at 8:30, we know from the question that these two targets need to meet or be in their respective positions at the same time. So that means that the time for R2 must also be 08:30. So now we know that this vessel B, which is the next thing we're going to be dealing with now, vessel B has got a relative vector over here, BO2, that we've already calculated to be 134 degrees true by 17 miles. So that's what vector B is doing. And then we also know what O2R2 is, because O2R2 is basically just the target maintaining its speed of 10 knots for 2 hours, which means that becomes 20 miles. So that's 50 degrees true by 20 miles, which is the same as that, because these two lines are equal. So that means that O2R2 then is also going to be 050 by 20 miles. So we've got a direction and a distance there. And we got a direction and a distance there, which means we can find a direction and a distance for the vector BR2. So in this case, what we can do, if we have a look at our vectors again, so it's similar to what we've done with these first two when we looked at the resultants. We're saying, well, this vector here, BR2, that we're trying to find, is going from B to R2, and in a similar way, we're going to taking the two remaining vectors going from B to O2 and then from O2 to R2. So it's clear that the resultant is this top one. So the resultant is BR2. That means that the vector BR2 is going to be BO2 plus O2R2. So again, if you've got a calculator that can add vectors, you can do that. And if you need to then work that into an X and Y rectangular coordinates, then you can also go that route. It should get you a similar answer. So the vector BR2 basically is those two vectors added together, like we said. So it's going to be BO2 plus O2R2. Now in this case, and if you look at the top here, I said we can come back to this earlier. So there's that 2 hour again, that 2 hour change in time. So in both triangles, the change in time must be the same. and because it's 17 miles and we know it's in 2 hours, that means it's 8.5 knots. So we can either convert this into a speed as well for this BO2 vector, and we've already got a speed for the target here as well, which means we can get that straight into a speed. That BR2 vector is going to give us a speed, or we can work with distances and then divide it by the 2 hours again afterwards. So in this case, we might as well just work with the speeds. So we're going to have 134 by 8.5 knots, which is this BO2 vector, plus the target's actual vector of 050, because we know that it's the two combined. And if we add all of that up, it's going to give us a course of 088 by 13.8 knots. So that basically tells us now that we've got both of these targets now sorted. So target B needs to maintain a course of 088 degrees true by 13.8 knots, and that's going to be for 2 hours, which means that in 2 hours time at 8:30, at the same time as R1, this vessel, this target B, will be in position R2. So now we've got vessel A at R1 at 8:30, and we've got vessel B at R2 at 8:30, and that essentially solves our question. So the only thing that's left that we need to do that was in the question was basically the part where they said towards the end, saying find then the position, the actual position of the on-ship or the on-scene commander once both targets are basically on station at required. Now in this, that part is relatively easy. So that's saying we're starting at a position of 36 degrees 25.1 minutes north by and 125.06.9 east, and we know that we are proceeding at 050 degrees true at 10 knots, which we now know we will be covering for 2 hours between 6:30 and 8:30. So it's basically going to be 050 by 20 miles. So from there you can simply do a plain sailing calculation. You do a plain sailing calculation saying, well, if you're starting at position A over here and you are steaming 050 by 20 miles, then you can work through plain sailing, take this vector, then work it into its rectangular and polar coordinates, or its rectangular coordinates rather, its x and y coordinates, which we know will be a d latitude and a departure. Work that into a d long, and then you can simply apply that to this initial position, and that will give you then the final position for the on-scene commander at the time of rendezvous for both other ships. And that essentially answers an entire rendezvous question. So I really hope this has helped you, and that it can assist you when you're trying to attempt these questions at home.